This is a video walkthrough for practice 10.3, sigma notation and series. In number 1, we have the summation of f of n as n goes from 4 to 7. So that means that we start with f of 4, so in other words replace n with 4, and then count upward, plus f of 5, plus f of 6, plus f of 7. In number 2, we're starting our counter at 0, so replace j with 0. That would be 2/3 to the 0, plus 2/3 to the 1, plus 2/3 to the 2, plus 2/3 to the 3, because 3 is the upper limit of summation. In number 3, we're writing in expanded form. So this time there are a number of terms, right? We're going from k equals 6 to k equals 73, so we're going to use ellipsis. And the directions state that when there are a large number of, or an infinite number of terms, write the first 3 terms before writing an ellipsis. So we're going to start with 6 to the 5th power, plus 7 to the 5th power, plus 8 to the 5th power, and then plus ... our ellipsis, and then plus, and now you can write the last term, which would be 73 to the 5th power. In 4, we have the summation of a sub n as n goes from 3 to 7. So replace n with 3 to start with, and then add, replace n with 4, with 5, with 6, and with 7, and we're summing them all. In number 5, j goes from 7 to 10, so the first term is 1 over 7 squared, second is 1 over 8 squared, third term is 1 over 9 squared, and the last term is 1 over 10 squared, and we're adding them all together. In number 6, we have a summation that starts at k equals 3, so the first term is 3 plus 1 over 3 squared, and the second term is 4 plus 1 over 4 squared, and the third term is 5 plus 1 over 5 squared. We've listed 3 terms already, and so at this point, since there are an infinite number of terms, we can just write plus ... at the end. All right, in number 7 through 10, we're evaluating the summation. In number 7, we can create a table to help for this summation and list the n values, which go from 1 to 5. So 1, 2, 3, 4, and 5. And then in the second column, list the values of the terms, which are equal to 2 times n plus 1. If n is 1, 2 times 1 plus 1 is 3. If n is 2, 2 times 2 plus 1 is 5, etc. And so this summation is 3 plus 5 plus 7 plus 9 plus 11, which equals 35. In number 8, we can use a table to help for this summation. The index of summation this time is m, and m goes from 0 to 3, so 0, 1, 2, and 3, and the value of the terms are equal to 2 times 5 raised to the m power. If m is 0, the value is 0. If m is 1, 10. If m is 2, 2 times 5 squared is 50, and then if m is 3, 2 times 125 is 250. And so this sums to 2 plus 10 plus 50 plus 250, which is equal to 312. In 9, we have the summation of k squared minus k as k goes from 2 to 4. So I'm going to create a table to help. The index of summation is k, and that will number from 2 to 4. And then we find the value of k squared minus k. If k is 2, that's 4 minus 2 is 2. If k is 3, that's 9 minus 3, which is 6. And if k is 4, that's 16 minus 4, which is 12. So this summation is equal to 2 plus 6 plus 12, which is 20. In number 10, we have the summation of p divided by p plus 1, where p goes from 1 to 4. And so our counter, or index of summation, is p. That will number 1, 2, 3, 4. And then the second column can be p divided by p plus 1. If p is 1, that's equal to 1/2. If p is 2, 2/3. If p is 3, 3/4. And p is 4, 4/5. So then we can add all of those terms together, and you are welcome to use your calculator to do this. And that value is 163/60ths. Make sure that if you're using your calculator for this, that you have your calculator in exact mode, where it's going to give your answers in fractional forms rather than decimals. In 11 through 18, we are asked to write each series using sigma notation. 6 plus 9 plus 12 plus 15 is an arithmetic series, and it has a common difference of 3. In those cases, a sub n, the general term, is always equal to the first term plus the common difference times n minus 1. Our first term is 6, and our common difference is 3. And so if we simplify this expression, 6 plus 3n minus 3, that's going to give us 3n plus 3 for the general term. Since there are 4 terms, this is written as the summation as n goes from 1 to 4 of the general term 3n plus 3. In 12, we have a geometric series. Each term is the previous term times -2, so our common ratio is -2. And in a geometric series, the general term a sub n is equal to the first term times the common ratio raised to the n minus 1 power. And so the first term is 5, and the common ratio is -2. And so that's our general term. So this can be written as the summation as n goes from 1 to 5, since there are 5 terms, of 5 times -2 raised to the n minus 1 power. In number 13, this is a series that is neither geometric nor arithmetic, but you will recognize that each number in the each term of the series rather is a perfect square. So we can approach this with a table, and I can let n equal 1 through 6, since there are 6 terms. And the value of the term a sub n would be 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, and 10 squared for each term. And so in those cases, what we'll notice is that each term is 4 more than the number of the terms squared. So that would give us an a sub n equal to n plus 4, the quantity squared. And so this would be the summation as n goes from 1 to 6 of n plus 4 squared. Now that's one way to do this, but if you like, you can take a second approach, and if you notice that your terms are starting with 5 squared, 6 squared, 7 squared, etc., then we can just make our n start at 5, 6, and 7, etc., and we would end with a term number 10. So in that case, we can write a different summation. That would be the summation of n squared as n goes from 5 to 10. Both are equivalent and both are correct answers. In 14, we know that this is an arithmetic series, and so in an arithmetic series, a sub n, the general term, is equal to the first term plus the common difference times n minus 1. And so the first term is 1, the common difference is 7, and so that means our a sub n is equal to 1 plus 7n minus 7, and a sub n is equal to 7n minus 6. The thing that we don't know is, although we're starting at the first term, we don't know what number term this is. So I'm going to replace the term value with 323 and then solve for n. So adding 6, that would be 329, is equal to 7n, which would give an n value of 47. And so when we write our series in sigma notation, the general term is 7n minus 6, and the counter, or the index of summation, goes from 1 to 47. In number 15, this is neither arithmetic nor geometric, but you will notice that each of these terms is a perfect cube. And we do start with 1 cubed, and then go to 2 cubed, 3 cubed, 4 cubed, and we're ending with 10 cubed. So this is going to be the summation of n cubed as n goes from 1 to 10. In number 16, if we look at the ratios of the terms are 28 divided by 4 and 196 divided by 28, etc., which are all equal to 7. So this is a geometric sequence series, since we're adding them together, with a common ratio of 7. In a geometric series or sequence, the general term is a sub n is equal to a sub 1 times r to the n minus 1 power. So this is equal to 4 times 7 raised to the n minus 1 power. And we don't know, however, what term number this very last term is, since there are ellipses. And so I'm going to replace that a sub n with 161,414,428, and then solve for the value of n, or the number of the term. In order to solve this equation, we need to begin by dividing by 4, which gives us 40,353,607. If we want to solve for the exponent is equal to a logarithm. So the logarithm is base 7 of 40,353,607, and then adding 1, n is equal to 1 plus the logarithm base 7 of 40,353,607. That should give us an n value of 10. So in this case, when we write in sigma notation, this is the summation of the general term 4 times 7 raised to the n minus 1 as n goes from 1 to 10. In 17, this series is neither geometric nor arithmetic, but if we look strictly at the denominators of each fraction, the denominators form an arithmetic progression. So the denominators are equal to the first term of the denominator, which is 3, plus the common difference of the denominators, which is 4 times n minus 1. Simplifying, 3 plus 4n minus 4 is equal to 4n minus 1. So our general term for this series is 1 divided by 4n minus 1, since the 4n minus 1 gives us the value of the denominators, and 1 is always the value of the numerator. In this case, we're assuming starting at 1, there are 5 terms, so that means that we're ending at 5. So this is the summation of 1 over 4n minus 1 as n goes from 1 to 5. In 18, these fractions form neither an arithmetic nor a geometric sequence. However, the numerators, if we look strictly at those, they are forming an arithmetic sequence. So I'm going to write an expression for the numerators. So the numerators are equal to the first term of the numerator plus the common difference times n minus 1. And so that gives us 3 plus 2n minus 2, which is 2n plus 1. The denominators of each fraction form a geometric progression where the first term is 2, and then the common ratio is also 2. So this would be a denominator of 2, the first term, times the common ratio 2 raised to the n minus 1 power. Remember that there's an understood exponent of 1 on that first 2, so when we multiply like bases together, we keep the base and add the exponent, so the denominators are 2 raised to the n power. So that means that this series written in sigma notation is the numerator 2n plus 1 divided by the denominator 2 raised to the n power, as n goes from 1 to 5, since there are 5 terms. In number 19, we're going to write in expanded form the sum as n goes from 1 to 3 of 4. So that means the first term is 4, the second term is also 4, and the third term is also 4. So in other words, 4 is a constant, and so that means the terms don't change, they are always 4. 4 plus 4 plus 4 is the same thing as 4 times 3, which is 12. In number 20, the sum as n goes from 1 to 5 of 4 is 4 plus 4 plus 4 plus 4 plus 4. And so that's the same as 4 times 5, which is 20. In number 21, this is 4 plus 4 plus 4 plus a whole bunch of missing terms, so I'll use my ellipsis, and then we're ending with 4. Now, how many 4s are we adding together? There are 70 terms, so this is the same thing as 4 times 70, which is 280. In number 22, since this is a constant term, 4 plus 4 plus 4 plus 4 plus some missing terms, and plus that 300th term, 4. This is the same thing as 4 times 300, since there are 300 terms, so that would be equal to 1200. In number 23, the arithmetic series 369 plus a whole bunch of missing terms plus 144 plus 147 plus 150 is a series that has 50 terms in it. You'll notice that the first term is 3 times 1, and the second term is 3 times 2, and the third term is 3 times 3, and so our last term is 3 times 50. That's why maybe the number of terms might have been obvious. The series was written below twice, right underneath each other, forward and backward. So we're going to write a series below by adding the two series together, by adding those terms that are aligned vertically. So 3 plus 150 is 153. 6 plus 147 is also 153. 9 plus 144 is also 153. In fact, every pair of terms, when they are arranged like this, forward and backward, right underneath each other, adds up to 153. Now, you'll remember from the previous problems, when we have a constant that's added to itself 50 times, that is to say there are 50 terms here, that this is equal to 153 times 50, which is equal to 7,650 or 7,650. Now, that's not the answer to the question, though. The answer to the question is, what was that original series, the one that we wrote both forward and backward, equal to? Well, the 153 plus 153 plus 153, etc., that was the sum of two of those series. So the sum of the original series should be 7,650 divided by 2, which is 3,825.